Let's talk about determinants. Recall that this is how we define the inverse of a 2 by 2 matrix. If B is the matrix ABCD, then B inverse is 1 over AD minus BC times this matrix. Okay, so you switch the A and the D. You got a D here, you got an A here, and then you stick negative signs in front of the B and the C. So B inverse is going to be this matrix. B inverse exists if and only if AD minus BC does not equal 0. So B is invertible if and only if the determinant of B does not equal 0. This recalls what we call the determinant of B. We want to extend the definition of determinants to larger square matrices so that they will also have this property. In other words, we want to define the determinant of an n by n matrix A in such a way that A is invertible if and only if the determinant of A does not equal 0. Let's start with 3 by 3 matrices. Suppose A, we'll define A in this way, is invertible. Assume that A11 does not equal 0. If it is, exchange rows so that the new A11 does not equal 0. Via Gaussian elimination of this presumably invertible matrix, we get this. Holy cow! Gaussian elimination, you can verify this. It'll take you 45 minutes, but this is what you end up with. This is where delta equals this really hairy expression. Now, if A11 A22 minus A12 A21 is 0, this is not going to work, so we'd have to switch rows 2 and 3 at the beginning. If A is invertible, or sorry, I should say since A is invertible, the bottom row can't be all zeros, and thus delta, that can't be 0. So we've got it. The converse is also true. If delta does not equal 0, then A is invertible. Because if delta is non-zero, that means that implies that AX equals 0 has only the trivial solution, which implies that A is invertible. We're going to define delta to be the determinant of A. So the determinant of the 3 by 3 matrix A is going to be delta, where delta is this humongous expression. Then determinant of A can be calculated using either cofactor expansion or, in the case of a 3 by 3 determinant, the basket weave method. We are not going to have to memorize this. That would be crazy. Find the determinant of the 3 by 3 matrix A, where A equals 1, 2, 3, 4, 5, 6, 7, 9, 10, and we're going to use what's called cofactor expansion. Okay, the determinant of A is 1. We're going to expand along this top row. It's 1 times the determinant you get when you cross at the row and column of 1. That looks like 4, 6. That looks like, that's going to be 5, 6, 9, 10. And then minus 2 times the determinant you get when you cross at the row and column of 2. That's going to be 4, 6, 7, 10. Now you may be wondering, gosh, why does he have the minus sign there? I'll explain that in a moment. Plus 3 times the determinant you get when you cross at the row and column of 3. And that's going to be 4, 5, 7, 9. So this is that's the value of the determinant, the 3 by 3 determinant. Let's calculate that. Okay, so we have 1 times 50 minus 54 minus 2 times 40 minus 42 plus 3 times 36 minus 35. In other words, it's going to be 1 times negative 4 minus 2 times negative 2 plus 3 times 1, and all of that works out to be 3. So that is the value of the determinant. Now, the determinant we get when we cross at the row and column of 1 is what we call the minor of 1. So this thing here, 5, 6, 9, 10, that's what we call the minor of this entry 1. We denote it by A11. Some authors denote this by M11. Thus, the determinant of A looks like this. So it's going to be little a11, which is, in other words, is 1, times the minor, okay, 5, 6, 9, 10, minus 2 times the determinant you get when you cross at the row and column of 2. So that's going to be 4, 6, 7, 10. That's the minor, capital A1, 2, plus 3 times the minor of 3. In other words, 4, 5, 7, 9. And that's the minor of 3, 4, 5, 7, 9, capital A1, 3. Okay, now I'm going to tell you where we get the plus minus plus pattern. Actually, when we're calculating the determinant, we can use any row or any column. We used the first row, didn't have to do that. We decide whether to put a plus or minus in front by using this checkerboard pattern. So, for example, let's evaluate A by expanding along the second column. So we're not going to do the first row, we're going to do the second column. We're going to get negative 2. You might ask, why is it negative? Well, it's the checkerboard pattern. Negative 2. So it's negative 2 times the determinant you get when you cross the row and column of 2. We saw that earlier. That's just going to be 4, 6, 7, 10. Plus 5. Why is it plus? Plus minus plus pattern, plus 5 times the determinant you get when you cross the row and column of 5. Okay, that's going to be 1, 3, 7, 10. That's the determinant you get. Minus 9, again, plus minus plus pattern. It's going to be a minus 9. Minus 9 times the determinant you get when you cross the row and column of 9. So that's going to be 1, 3, 4, 6. So when we evaluate this determinant, we get negative 2 times 40 minus 42. We saw that earlier. Plus 5 times 10 minus 21. Minus 9 times 6 minus 12. In other words, it's negative 2 times negative 2 plus 5 times negative 11 minus 9 times negative 6. 4 minus 55 plus 54, which is 3. And that's what we got earlier. We can incorporate the plus or minus with the minor a sub ij and call the whole thing the cofactor, c sub ij. So the cofactor is just a sub ij with the plus or minus in front. So in this case, we saw earlier the determinant was this, little a11, capital A11 minus little a12, capital A12 plus little a13, capital A13. We can just designate it like this, A11, C11, A12, C12, A13, C13, because the C12 is negative A12. It's got that plus minus plus already baked into it. In general, C sub ij is going to be negative 1 to the I plus j times aij. And again, this technique that we're using when we evaluate matrices in this way, this is called cofactor expansion. A square matrix with a row or column of zeros has determinant 0, because if you expand along that row or column, you're just going to get a lot of zeros. Evaluate this determinant. Okay, you'll find that it's 30. All of the entries below the main diagonal are 0. Such a matrix is called an upper triangular matrix because the only stuff that's important is in the upper triangle of the matrix. In a lower triangular matrix, all the entries above the main diagonal are 0. A matrix which is either lower triangular or upper triangular is triangular. And the determinant of a triangular matrix is the product of the entries along the diagonal. So in this case, 3, 5, 2. So we could have just, knowing that it's a triangular matrix, we could have just calculated that the determinant is 3 times 5 times 2. Now there's another way that we can evaluate 3 by 3 determinants called the basket weave method. Recall how we evaluate 2 by 2 determinants. We saw this a moment ago. Okay, it's going to be the product of these minus the product of these. There's a similar way to evaluate 3 by 3 determinants. For example, let's find the value of this determinant we saw a moment ago, 1, 2, 3, 4, 5, 6, 7, 9, 10. Copy the first two columns. You got a 1, 4, 7 and a 2, 5, 9 here, copied from here. Let's look at the sum of these products. So just like we did with 2 by 2 determinants, we're going to take the sum of these products. So 1 times 5 times 10 is 50. 2 times 6 times 7 is 84. 3 times 4 times 9 is 108. And we just add those up and get 242. Minus the sum of these products. So 7 times 5 times 3 is 105. 9 times 6 times 1 is 54. 10 times 4 times 2 is 80. That's 239. So the sum of these products, 242, minus the sum of these products, 239, is going to be our answer. So 242 minus 239 is 3. But remember, this only works for 3 by 3 matrices.